Okay, here we are with our PowerPoint for 3.2.2, Loads and Paths. You should be taking notes on this in your engineering notebook as we go. This PowerPoint is going to talk about structural design and specifically our loads and how to calculate the loads that are going to be affecting our library. Here's our steps for our structural design, and as I said, we're going to be talking about establishing what the loads are. How do we calculate the loads we're going to be encountering? So this is what we need to think about. What kind of loads we need to include, and guess where we're going to look for that information? That's right, our favorite place, the codes. First of all, we have dead loads, and we've kind of talked about this before. We're talking about the weight of the building components, the weight of the building itself, and fixed service equipment, like you can see this equipment in this picture right here. Generators, air conditioners, water heaters, all that sort of things. We also have to talk about live loads. That includes loads that include the occupancy or the people in the building, also things that could be moved around. And then we have our design loads. For instance, snow. Our library is going in Indiana, so snow is actually a factor there, and we'll be looking at that. We also have to consider exposure to wind, importance of the building, and when we say importance of the building, we could mean historically important, but we value things like schools and places where we're going to have large congregations of people as being very important. This is a very important slide right here. You need to take a minute and copy down this formula as well as what each one of these variables means. We will be using this in the activity. And it looks like a long formula, but basically these are all factors that we'll just be looking up or will be given in our problems, and then it's just straight multiply them. So design snow load. So we'd have to look in our codes to find a map that'll tell us what the loads are. For instance, in Springfield, Colorado, where the red dot is right there, the load is 15 psi, and we can see it right, PSF, which we can see right here. So our minimum snow load, where PG is less than 20, 15, that's 15, so it's less than 20, so our PS is more important than this. If PG is greater than 20, then PS has to be greater than IS times 20 SPF. We'll see some examples with this, and hopefully this will become a little bit more clear how we use each one of these. Design loads also include all of these lateral loads. When we say lateral, we mean sideways loads. Wind, earthquake, floods, earth pressure down here pushing on the sides of our footing. Wind, we have the sideways where the wind is coming from pushing on this side, but when the wind is going this way, it also creates a suction or a low pressure on this side, which we have to account for. Also, as the wind pushes on this side, it literally creates a wind foil, which is what airplane wings look like, which pushes down on this side and lifts up on this side. We don't want our roof to rip off of our house, so we have to take the wind into consideration. Earthquake loads. They'll be different importance in different areas, but they affect our building. Flood. We've seen a lot of flooding in the last few years. It is an important factor. We don't want our building to literally be swept away if there's a flood. And design loads. If we have a basement or a part of our footing that goes below the ground, the soil is creating pressure on those underground portions, and we want to make sure that they don't cave in. Load types. Uniformly distributed load. For instance, snow on our roof, it's very even across the roof, versus a concentrated load might be we have an air conditioning unit on top of our building. Load combinations. So buildings will have some combination of all those loads we talked about. The codes actually tell us what kind of loads we need for the kind of building we're dealing with. For example, it might be dead load, plus live roof load, or snow or rain, and different combinations. So you can kind of look at what each one of those symbols means and some different examples. Again, we get it from our favorite thing, the codes. So here's a few things just to think about. The building dead load is the only known load that we have. All other factors will vary depending on location, and even throughout the year those things vary. That's why we call them live loads. And the building is designed for loads more than we hope will ever occur. We want to design so that our buildings are safer than any disaster that will ever happen to them. It's always our goal. Load paths. This is really important. This is what we're going to be working on. Our loads, a lot of our loads come here on the roof, but we also have loads on each one of our floors, and you can see it by the little arrows going down. And what happens is these loads travel down until they reach the ground, until they reach the footing. So the load that's on the roof travels down the roof and goes to these columns. The load on this part where perhaps an HVAC or an air conditioning unit is, it travels along the floor and beams over to these columns. And our loads on each one of these floors also travel along the floor, along the beams, and then down our columns. So we have to figure out what's our load on our roof, then we put that load onto our columns, then we put that load onto our footings. So we'll be doing each one of those parts separately over the next few classes. Okay, this is another picture kind of showing the same thing. We have our loads, for instance, in the middle of this beam. The load goes onto the beam. We have to design how big a beam we need. Then all these beams push on this girder, so we have to decide how big this girder needs to be. Then the girder pushes on the column. How big does the column need to be? And finally it pushes on the footing. How big does the footing need to be? So I'm just going to let you look at this. This is the same thing we just talked about. All these items have to be calculated separately. And they call this load chasing. That's what I just described, as it goes from floor to beam to girder to column to footing. Here's these same parts. Beams. These are girders. So what's the difference in girders and beams? Well, girders usually have several beams that are putting the weight onto them. So this is a girder. Looks a lot like a beam. Columns go up and down, footings at the bottom. Okay, I gave you a paper like this. It actually has two of these pictures on here. You're going to use one to do this example that I'm about to show you in the PowerPoint. So if we want to calculate how much weight is going on these beams here, we start with the area we're going to design for, like this part right here. And I'm not going to worry about the entire floor. I'm just going to design how big one of these beams is here. So I have to look at my dimensions on my picture. This is 18 foot long. And then I have a spacing here of 20 foot, and if I divide that in 3, I get each of these 6 foot 8 inches. So there's 6 foot 8 inches in between these beams. But when I think about a beam, the part on this side right here is going to go toward this beam, and the part on this side is going to go toward that beam. So we're dividing up the amount of floor space so that it goes with the beam that's right in the middle of it. To figure out how wide this is, it's just a little bit of math. If the distance between beams is 6 foot 8, then half that distance is 3 foot 4, and so that makes this area that's going to go onto this beam 6 foot 8. They call that tributary width. Tributary, like tributary rivers, they move into a larger river. This is our width that's going to be a tributary and lead all that weight into this beam here. Define the tributary area, length times width, right? Length is 18, width is 6 foot 8 inches. Calculate that up. What is actually our tributary area? Take a minute and do that on your calculator on your notes. Okay, so now we have this width here, and they're calling this beam B3. Should make kind of sense because that's right here beside B, and that's right here beside 3. So again, we now need to take our floor loading PSF times the width to find our beam uniform load. You should be writing down each one of these formulas as we go through each one of these slides. We will be using these later in our activities, so be sure you're writing these down. So our tributary area that we saw on the slides before, 18 foot long, 6'8" wide, which they converted over to just feet. So our tributary area is 120 feet squared. And now we're going to calculate that beam loading we saw a second ago. The total floor load, assume that the floor system supports its own weight, which is 40 PSF dead load. That's 40 pounds per square foot. So if I take a square foot, 1 foot by 1 foot square, that's 40 pounds right there. And we're going to have a live load also of 100. So the total loading, we just add the dead plus the live to get 140. Then the uniform load is the floor load, 140 from right there, 140, times the tributary width. Notice that's the width, again, converted to feet. So we get a uniform load of 934 pounds per linear foot. Okay, now we're going to look at the girders. So use the other one of these blank pictures I gave you to do these notes. So now we're talking about the girders here, this girder. And for this girder here, notice you can see the I-beams where it ends in each one. It's 20 foot long, and 1, 2, 3, 4 beams are all going to this girder. Notice they are making a difference on this interior girder versus this exterior girder. Here, I only have beams coming from one side. Here I have beams coming from both sides onto this girder. And then I have a column here. This girder, and these beams are all going directly onto this column. So we're going to look at this and use this for calculating column loads here. And basically what they do is they take halfway between this column and find this length here. And halfway between this column and find this distance here. And then use a length times width to find that tributary area for that column right there. Assume the floor system must support its own weight of 40 PSF and 100. So this is the same numbers we saw in the last one. And now we're going to calculate the columns. So again, add the dead and the live, 140 PSF. Column load, tributary area, 360 square foot. That's what we got on the previous slide. Times the dead, times the load we have right here. That's the load we have right there, to get the column load right here. Be sure to copy these down onto your notes. So this is the same list that we saw at the beginning as we were calculating that. Bring me your notes to show me your notes, and then start on the activity. Thanks for watching.